Okay, we need to finish this problem. I started it last time and had to break, so we're going to redo it now, or pick back up where we left off. So we had just finished finding the moment equations for the structure, and now we're going to use virtual work. Since we want to know the displacement at point C, we're going to have to do a virtual system with the virtual force at point C. So I will assume, or not assume, I'll go ahead and draw my structure with my virtual load. There you go. At point C, I'll assume it's acting down, so my force is down. And since I've already established origins for my moment equations with the real moments, I'll just repeat these free body diagrams for the virtual load. So just to help it look a little better, I'll just draw a line here. So now we'll start with the same as before. We'll start with section AB, and my free body diagram will look pretty much the same. Geometry is the same, making the same cut as before, except now the load at the end is just 1, my virtual load. And I'll still assume it goes down in the Y direction. And then at the bottom, I'll have now my virtual moment in AB and my virtual force in AB. Okay? So, this was 10 feet. Forgot to put that in there. So just as before, we'll sum moments about the cut. Again, I'll use right-hand rule as my sign convention for moments. We'll make sure everything's in equilibrium. So I'll start with the moment itself. That creates negative moment. So I'll have minus the virtual moment at AB. And I'll have the virtual force also creating negative moment with a moment arm of 10 feet. So it looks like my virtual moment in AB is simply just equal to negative 10. And strange units, just feet. Because we're saying our virtual force has no unit. And we'll go ahead and, oops, sorry, got the page twisted. We'll go ahead and sum forces in the vertical direction to solve for our axial force AB. That's acting down in our system. Other forces acting in the system are the virtual force also acting down. So it looks like our force AB is equal to minus 1. So it looks like, due to the virtual load, the axial force in AB is in compression, which makes pretty good sense. All right, now let's go to the next section. This will be section BC. We already know what our free body diagram looks like, the geometry of it, I should say. We're using a coordinate system from the free end, which we called x1. And now on that free end we have our force 1. And internally we have the virtual load BC, and then the virtual axial force BC. And you see these two are very similar. In fact, superposition will tell you that I can get these results simply by taking the real system and dividing it by 10. But I'll go ahead and do the equilibrium equations just the same. So we'll sum the moments at the cut, make sure they're in equilibrium. So I have this moment, which is negative, so that's the virtual moment in BC. And then the moment about the cut due to the virtual load, which is also negative, has a value of 1, and then a distance x1. So it looks like an equation for the virtual moment in section BC is going to be equal to minus x1. You can see symmetry shows that. If I divide the real moment by 10, I get negative x1. So that's good. Next we will sum forces in the x direction. I'll assume to the right is positive. So I'll have the sum of my forces in the x direction. And you can see I have internal force BC, and that's it. So it looks like the virtual force in BC is 0. So there won't be any contribution to the displacement at C through the axial force in BC. Okay, so I filled that page up. I'm going to have to do a little sliding around here. So I'm going to have to push this up out of the way a little bit. And then now what we need to do is combine all of these into our virtual work equation. So the displacement at C, in this problem EI is constant, so I'll just factor that out. So we'll have, and right now I'll just keep it as symbols. So the first section will be the section from A to B, and that has, you can see from our previous problem, I'll just look at the virtual part here, AB varies in the y direction from 0 to the bottom, which is 20 feet. So I'll have an integral from 0 to 20 of the real moment in AB times the virtual moment in AB, and that will be integrated dy. And then I'll add the second section, which was along this direction. That's AB. I'm sorry, that's here's BC. So we're going to integrate that in x1, and that's going to vary from 0 to 10. So I'll have an integral from 0 to 10 of the real moment in BC times the virtual moment in BC, and that'll be dx1. And there's the form of my equation. So now I just need to put everything in. So again, I'll keep my value of EI constant. Let's look at the first integral from 0 to 20. The real moment in AB, if we look back, is equal to minus y squared over 4 minus 100. And the virtual moment in AB is minus 10. Plus the integral from 0 to 10 of the real moment BC, which is minus 10 x1, and the virtual moment BC, which is just minus x1. That'll be dx1. And we'll close up the bracket on that. So now it's just a matter of doing integration. Now in class, most of you guys we've already talked about before, this is really enough. We could stop at this point and say, well, you've created the virtual work equation, just need to process it. Since we have time here on homework and in class, we'll go ahead and try to finish this up. So right now I'll still keep my EI constant, not worry about that for a moment. And let's see what all this will give us. So let's do this integral first. So I have minus y squared over 4 times 10. So when I integrate that, I'll get y cubed over 12 times 10. I'll just write it out. So I'll have 10 y cubed over 12. Minus minus makes that positive. And then this also becomes positive. That's just 1,000. And when I integrate 1,000, I get y. So that little chunk needs to be evaluated from 0 to 20. And then plus, this term also has the EI constant. And this is just 10 x1 squared. So that becomes 10 x1 cubed over 3. Oops, sorry. Need to take these things down, I think. And that's evaluated from 0 to 10. All right, let's see if I can process this for you. Let's see what we get. To get out my calculator, just give me a second. Find it. All right, so we'll put 20 in here. So I'll have 20 cubed divided by 12 plus 20,000 times. Add those two together. Looks like I get 20,667. That's that term. Plus this stuff over here. And that's just 10. That's 1,000. That's 10,000 divided by 3. And we know 10,000 divided by 3 is just 3,333.3. I don't know why I put that bracket there, but I'll close it up anyway. So if I add those two together, looks like I get exactly 24,000. And the units are going to be kip feet cubed and then divided by EI. Hopefully I did that right. Probably have to check this later. So let's go ahead and do the numerical value. So I have 24,000 kip feet cubed. And I need to divide by E and I and do conversion. If you look back on the previous problem, our E value was 29,000 kips per inch squared. That's steel. The given I value was 1,000. Pretty healthy size section. And then the cubic feet would be 1728 or 12 cubed inches cubed per foot cubed. So let's see what we get for that. 29,000 divide 1,000 divide 1728 times. I get 1.43 inches. That doesn't seem outrageous. Oh, and I'll have to check that later, but I think for now that's good enough for us to look at. It doesn't seem unreasonable that beam would bend about an inch. And that's vertical. And we got a positive value, so it did go down. Okay. I'll stop here. If I find an error in this, I'll post it later in the class.